Good afternoon, everybody. We have had many editions of this journal club at Physical Review Fluids, but I think this is the first one dealing with taxis and with issues related to mixing. So we're very happy to have this topic today. The topic will be served by Robin Einonen in connection with a paper co-authored by himself, Luca Biferale, Antonio Celani, and Massimo Vergasola. This is about optimal trajectories in turbulent flow related to searches. Well, Robin, you're on the floor for 15 minutes, and then those having questions are invited to raise their hands in the chat. All right, Robin.
All right, well, thank you very much for the introduction and generally speaking for the opportunity to speak about my work on olfactory search. So let me just jump right in. So what is olfactory search? The problem we have in mind is that we imagine that there is a source of odors or some other passive scalars which is embedded somewhere in a turbulent flow. And we have an agent somewhere which is sensitive to these odors and uses local concentration measurements in order to move and track the source in a minimal possible time. And the main motivation we have in mind is that this is an important animal behavior for a number of flying insects and aquatic animals that rely on the behavior for mating and foraging. For example, moths, this is a very salient example. For mating, the female will sit on a tree somewhere and emit a single pheromone to which the males are very sensitive, and the males, smelling this, will begin flying upwind, using this pheromone to track the females, and they're able to do this on distances which can exceed 100 meters, which is quite extraordinary, especially considering the fact that on such macro scales, turbulence dominates the transport of passive scalars, which complicates this problem immensely. I'll note in passing, this problem also has some applications to biomimetic robotics. Suppose you want to build a drone to track a bomb or a leak of a hazardous chemical or something. So what are the effects of turbulence on this problem? So first of all, a concentration field of a passive scalar in a turbulent flow is going to fluctuate really wildly and essentially behave as a stochastic object, which means that in practice, the agent's encounters with the odor are going to be effectively randomized, and that it only will give partial and probabilistic information about where the source is. Moreover, the concentration field exhibits strong spatial temporal intermittency and long non-Gaussian tails. So what this means can be visualized, for example, in this plot here, which shows a snapshot from a jet flow experiment of a concentration field. And here the intermittency is realized by this sort of patchy landscape where you have some small localized regions of high concentration mixed over a background of essentially zero concentration. You can also see this in our own DNS simulations, which we'll use later. We also here have a time series at a single point downwind of a propylene source, showing the concentration. And here the intermittency is realized by the spikiness. We had these long periods of time on the order of tens of seconds with essentially zero concentration dispersed with spikes of high concentration. So what this means for the search is that typically we'll have no gradients to exploit, and what gradients there are will not instantaneously point towards the source anyway. And this rules out any simple strategies which are based on gradient climbing. A second consequence is that frequently the local concentration will just be measured as zero. And indeed, far enough downwind, where the problem is interesting, one can show that the encounters are in fact sparse. So altogether, we have sparse, randomized encounters with the odor and no gradients, which begs the question of how one can use this information to search effectively. So one can start by looking to nature for some inspiration. So this is what moths do. When they're in the plume and smelling something, they'll generally fly close to directly upwind. What's more interesting is what they do out of the plume, which is a stereotype behavior called casting, where they move in these broad crosswind zigzag motions while slowly flying upwind. This is a very well-known behavior. A little less well-known is it's sometimes reported that after a really long time without smelling anything, the moths will sometimes turn around and begin flying back downwind. So the focus of this talk is what are optimal search strategies going to look like, and I'll define in what sense I mean optimal. And in particular, what is the relationship between such optimal strategies and these naturalistic strategies we see actual animals performing. And so to begin, we set up the problem in the following way. We have an agent living on a two-dimensional grid world. We're going to use three-dimensional data, but we constrain the motion to the two dimensions for both computational reasons and analytical tractability. And then we're going to hide a source somewhere at an unknown location. And every time step, our agent is going to make a binary local concentration measurement, by which I mean simply low or high with respect to some threshold. And then it's going to move by taking an action and moving to an adjacent grid point. We're going to assume that these measurements are governed by just a single time statistics and can be described by a single likelihood function, which we call P of 1 of x, where x is the position with respect to the source. And this simply gives the probability of the concentration instantaneously exceeding some predefined threshold. In particular, this means we're ignoring effects of correlations, although we've addressed these in a new paper, which in fact was just accepted to physical review fluids yesterday. So our goal is to try to use this concentration data somehow, or these measurement data, to try to minimize the average time of arrival to the source. So the way we do this is using Bayesian statistics. We suppose that the likelihood is known, and under this assumption, the agent can maintain a belief, or a posterior if you prefer, which is a spatial probability map on the grid world, which assigns a probability to every point in space, which tells us how likely we think the source is to be there. And then we evolve this belief according to Bayes' rule, which simply tells us that every time we make an observation, we should rescale the local, we should rescale the belief by the probability of making that observation conditioned on the source actually being in that location and then renormalizing. A very important point is, well, before I get there, as more observation data come in, it's a classical theorem that the belief will concentrate probability on the ground truth source location. An important point is how do we initialize this the search? We're going to assume that there is an encounter, in fact, at time 0, which is what incentivizes the agent to begin searching. And this has the effect of biasing the initial belief so that the prior is not flat, but in fact proportional to the likelihood. So now we need the likelihood in order to proceed. In the interest of being as realistic as possible, we simulated the 3D incompressible Navier-Stokes equations in a turbulent regime, imposing a uniform mean flow for 5 different values of the intensity of the flow. And this models the wind. And then we place a fixed point-like source of Lagrangian tracer particles, whose positions we then track in time. To obtain our likelihood, we just set up a quasi-two-dimensional slab containing the source and build a grid world on that slab. These yellow particles are the particles in the slab. And then it's a simple exercise to empirically compute the likelihood after imposing our favorite threshold. And the likelihood looks something like this for the 4 non-zero values of the mean wind. And as the U increases all the way up to 7.4 times URMS, which is the largest one that we studied, we get a more tightly and tighter confinement to a conical plume structure. So now, once we have your likelihood, the goal is to craft a policy, which is just a map from the current belief to an action that you should take. One approach you could use is to just define a heuristic, the most popular of which is infotaxis. So the goal of infotaxis is to try to maximize the information content of your belief, which is to say you take the action, which minimizes an expectation, the Shannon entropy of the belief. And it turns out this performs very well and leads to some complex, interesting strategies, but nevertheless, it is not optimal. To get an optimal policy, what we want to do is we want to minimize the time of arrival. So we model this by giving a reward to the agent at every time step of -1 until the source is found. And then formally, our objective function is something called the value function, which is a function of the belief parameterized by the policy, which gives the total expected discounted reward under your policy pi, conditioned on starting with that belief. What do I mean by discounted? Well, gamma here is just a number between 0 and 1, which measures the horizon over which we are optimizing. We want the horizon to be long, so we take gamma as close to as 1 as computationally feasible. Now, the point is that the value function corresponding to the optimal policy satisfies the so-called Bellman equation, which has the following generic form, which basically just expresses a recursive structure present in all these kinds of problems, which are called partially observable Markov decision processes. So the goal then is to solve this equation, which in fact is very hard because the belief lives in a high-dimensional space. But nevertheless, we did some work to show that indeed it can be approximately solved with a pre-existing technique called point-based value iteration, which is based on dynamic programming. And then once you have your value function, you immediately have an optimal policy. And then you can allow the agent to search according to this policy. And one of the immediate results is that most of the time the agent has made no encounters after time 0. To be more precise, we've measured the probability here that given that the agent has not yet found the source and it's still searching, what is the probability that it hasn't smelled anything since time 0? Well, that probability, as you can see here, is typically greater than 50%, if not 60, 70, 80%. So this tells us that most of the time we're in the absence of odor, and it's really important to optimize what to do in such a scenario. And this motivates looking at the so-called no-hit trajectories, which are the deterministic trajectories that you get when you don't smell anything after time 0. I'm just going to show what you get for the strongest wind case because it's very interesting. You see what the agent does is it begins flying upwind in doing these crosswind zigzags. And then at some critical time, which should happen in just a second, the agent is going to turn around and then go back, fly back downwind close to where it started. So we have kind of a casting-like behavior followed by a downwind return, which is very similar to what animals actually do, which is quite exciting for us. We can be a little more quantitative, and here we look at the mean square displacement over trajectories. Here, the solid curves are ensembles of trajectories with encounters. The dashed lines are the no-hit, what you get from the no-hit trajectory. You might notice that they correspond very neatly, which underscores the fact that the no-hit trajectory is playing an outsized role in the ensemble. And the key feature is as follows. So for the first 150 time steps or so, the agent is going to fly upwind. And you can note the characteristic scaling here where x squared goes as t approximately. So we have diffusive scaling in time. And similarly, in the y direction, we have these oscillations, which are characteristic of the zigzags. And again, the envelope of these oscillations approximately goes as y squared as t. I'll also note in passing, so at this critical time, the agent begins its downwind return, approximately ballistically. And note that the absence of this in the infotactic trajectory, which is otherwise similar. This is the main qualitative difference between the two. And so much of the remainder of the talk will be focused on where does this diffusive scaling come from? Can we derive it somehow? And so to this end, we first start getting an analytical expression for the likelihood in the large wind limit. So this was already a problem basically solved. And the result is that we have a factor that's it's a Gaussian factor which confines the likelihood to a cone, which with opening angle of URMS over U. And then secondly, we have this exponential decay along the downwind direction x, with characteristic decay length xd, which is the following form in terms of physical parameters. Here, S is the source intensity. And I'll just mention that this agrees very well with our simulation data. However, this doesn't work when you're very close to the source, so we need did some other analysis. So directly downward where the source is a small region, essentially 1, corresponding to the region where the typical concentration exceeds the threshold. And then we can show that that strip has a characteristic length, which we call L star. L star has the following scaling. It goes as U to the 2/3 and C threshold to the -1/3. Here, LS is the source size. And the upshot of all this is that for a sufficiently strong mean wind, the likelihood is going to be large on this little strip and relatively small everywhere else. And now what we're going to do is going to take this low information limit to the extreme, the limit of extreme sparsity. And that's with the limit where there are no encounters except when you're within this L star neighborhood of the source. And we're going to put one additional approximation on top of that, where we're going to replace our Gaussian confinement with an indicator function, so that we have exact confinement, and the prior has the following form, where f of x is just some function of the downwind distance. And so then as the agent moves around, it's just what it's going to do is it's going to have its prior, and it's just going to sweep out probability mass from its prior as it moves, basically until it finds the source. So under the simplified model, we can deduce what the optimal strategies can actually be, what they should be. First of all, if provided that our function f of x is monotonally decreasing, we can argue that the trajectory should be, in fact, be these upwind zigzags, because these are the kinds of motion that maximize the rate at which you sweep out probability. Then your problem asymptotically reduces to choosing a sequence of downwind positions where you want to perform the crosswind sweeping out. And it turns out that this discrete decision problem is exactly equivalent to a problem called the linear search problem, which is very well studied. And the upshot is that the optimal choice of these xi asymptotically obeys this relationship, which just says that the separation between consecutive points is in fact exactly L star. And it's a couple lines of work to show that this in fact gives us the diffusive scaling. Finally, what about the downwind return? Well, we argue that this results because the confinement to the cone is not in fact exact, and eventually it breaks down when you go far enough upwind. You reach a point where the prior is in fact comparable to the prior at some point close to where you started, just outside the cone. And at that point, you have no further incentive to keep flying upwind. As a final thing you can get from the low information limit is this tells us under this limit that the time of arrival is approximately the time that it takes a no-hit trajectory to reach a neighborhood of the source. And that we can then get an estimate of the arrival time PDF as the following integral, which simply expresses that fact. And we would just plug in our expression for the likelihood and the diffusive scaling, which we've already derived. And we get this characteristic stretched exponential form with exponent 1/2. And it turns out this agrees surprisingly well with our Monte Carlo data. On the plot, these are the PDFs empirically, and on this scale, this approximately linear relationship over a broad range of times is indicative of exactly this form right here. So in conclusion, odor sparsity is really important in the olfactory search, and a consequence of it is that the agent usually won't have smelled anything in a while. And this means you really have to optimize for plume loss. And when you constrain yourself to 2 dimensions, it turns out the optimal motion in this scenario is in fact casting, something that looks like casting combined with upwind flight and then followed by a downwind return. And this is very similar to what, in fact, animals actually do. It should be noted this is only true when the mean wind is large, which is the most relevant limit for flying insects, but you get other stuff at small and intermediate U. And we can understand all this by passing to the low information limit of extreme sparsity, which not only predicts these kinds of trajectories, but also gives us some non-trivial quantitative predictions, such as the arrival time PDF. So I'll mention finally that we have a future target for work is abandoning the model-based approach where we know the likelihood and doing a fully data-driven approach, such as Q-learning, which was the approach taken by this paper by Seminara's group, which is now my group, Genoa. And very finally, here are a list of papers for the interested parties on olfactory research that myself and others in Luca's group have produced in the last few years. Thank you very much for your attention.
Thank you, Robin. The formula for the return time to the source was awaited for a long time in this context, and we are happy to see one. This stretch
the PDF right here.
decaying exponential, yeah. I don't see any question in the chat, but maybe someone in the audience want to ask one. Otherwise, I have one for you ready.
Sure.
Yeah, so I think I mentioned this to you earlier. So that formula suggests that there is a decaying, uniformly decaying distribution of arrival times. But still, this is a distribution. So the time might be very large, but it has still it is still affected with a given probability. However, the experimentalists, in particular those who have made the earliest contribution to the field, like Alan Kardec, for instance, Ring Kardec, for instance, know that most animals, when they are released in the wake of a source, in fact, get completely lost and are never trapped in this exploitation system driving them towards the source. So the PDF, the experimental PDF, if you use many animals, is in fact a Dirac delta at infinity. And then for a few of them, a few animals, indeed, a distribution of arrival times, which might be well represented by your formula. So do you have an interpretation of this, or how do you understand that?
So my main comment is that probably these real animals are not Bayesian agents. We have a lot of computational machinery going into solving for an optimal policy. We have to maintain this. We have to maintain this posterior, and it's a huge computational memory intensive thing with thousands of grid points. And while allows us to compute an optimal policy for theoretical purposes, I don't think there's a biologist in the world that will tell you that this is probably what animals do, and at least small insects probably don't have a detailed spatial map that they're updating using Bayes' rule. And moreover, they probably don't have a perfect model of their environment, which is a real luxury to have. And one thing that happens one thing that you can find very quickly is that if you replace this likelihood with something that is not the ground truth, the agent will start failing. Also, we've constrained ourselves for 2 dimensions, which makes the problem easier. So we're really working in an idealized scenario in order to try to capture these optimal trajectories, but it's really putting a lot of pressure on the animals to actually do this. And I just think it's quite fascinating that nonetheless, what they've evolved to do something that is at least qualitatively very similar to what we find is optimal.
All right. Okay. So there's still work to do, right? Howard Stone had a question. Please, Howard. And then Ron Schnapp.
No, I talk too much, so let Ron speak.
Okay, so Ron Schnapp.
Hi, thank you very much for the interesting question. Thanks, Howard, for letting me speak ahead of you. I wanted to ask just a general question, like how sensitive is the insight that you've gained to the fact that this is turbulence? I mean, were this another kind of a stochastic process generating these plume, would you get the same kind of behavior?
So that's an interesting question. Maybe my interpretation is as follows. So the turbulence and properties thereof lead to these characteristic forms of the likelihood, right? Where they look something like this. And so really the point of the turbulence is getting these. And in fact, for this work presently, this is really the only input, and the agent is searching not for self-consistency, we decided to have the agent search not in the turbulent environment, but just in a stochastic environment derived from these likelihoods. Now, of course, the thing that's missing from this, besides this, is the correlations, that we have an actual turbulent flow is not going to look like this, like a Poisson point process, but instead there'll be patches and correlations and stuff. And it's a really interesting and complex question, which again we've tried to tackle, at least began to tackle in this paper that I mentioned earlier. And there's a lot of effects so turbulence tends to organize the passive scalars into filaments and patches. And this will tend to correlate successive observations on short time scales, which is generally a bad thing for a naive Bayesian approach, because you'll tend to overestimate, you'll tend to basically overcount the number of encounters that you make. On the other hand, we've found that, kind of interestingly, large-scale structures can help orient the agent closer to along the center line and navigate quicker, with the basic result being that for large enough wind, in fact, turning on the correlations makes the search faster, which was kind of a surprising and interesting result. But yeah, so let me say, if this is really what makes it turbulence and not just some other stochastic process that's generated by these likelihoods. Although those likelihoods did, in fact, are the result of turbulent physics themselves. I hope that kind of answers your question.
Yeah, it does. Thank you.
All right. We have a question in the chat by Ellie Stark. So you maybe you can read it, or if you can't, I can read it. This may be basic, but can you speak more about intuition for the extreme sparsity limit and how you can have optimal trajectories with no information? Does the domain boundary have any impact? Do the agents get turned around at boundaries?
Okay, well, that's kind of a multi-part question, so I'll try to answer one piece at a time. So first of all, let me just respond to the fact we said, how can you search with no information? It's not the no information limit, it's the low information limit. So you do gain information about where the source is, specifically by learning about where it's not. You are slowly sweeping out your cone of probability, basically. You know it's somewhere in this cone, and you're gradually sweeping out where it could possibly be. And because in the low information limit, in fact, the likelihood is 1 in the strip, you are in this idealized scenario actually determining with certainty that it can't be in these regions that you've already explored. So this is why you get these kinds of methodical zigzag strategies that just involve sweeping out the cone. This is my interpretation anyway. What else was there in this question? What was the second thing she asked? I forget.
The boundaries, the domain
the boundary of the cone, or the boundary of the box?
I think the question refers to the domain boundaries within, not the cone, but I mean, you could think of the wind tunnel if you were doing current.
I think you basically answered my question. Thank you with both, because it looks like that the agent was constrained to turn around within that cone. It's not like they had in some sort of infinite decision space or something. They had to remain within that as they kind of zigzag back and forth.
Well, yeah. So I mean, in this idealized scenario, there is no reason to go outside this cone. They can, but they won't, because we know that the cone is here. In practice, when we're not working in the low information limit, we do have a finite simulation boundary, but we try to choose it large enough that interaction with the boundaries essentially never happen, and that they're really providing a tiny effect.
That helped me understand the setup a lot more. Thank you.
All right. So we're close to the end, if not at the end of this session. Maybe Massimo, you want to add a few words?
No, thank you so much for the invitation, and it was a pleasure to attend. And thank you all for the questions you had.
All right. So we may stop here, Eric.
Yeah. Thank you, everybody, for coming.
Thank you for coming, and see you next time.